don't know him, but I got a very close friend in San Diego that actually passed away.
So currently I'm just predicting where the change is going to be.
Okay. And I saw an email from him. We were a very close friend.
So for that, I just have to do
Great. And then I realized he was involved.
So the first thing I'm interested in is what are the
He's one. With Mono, they were working on allosteric effect and then defined it.
It's amazing that had that insight into like whatever 1960s landing on more global structure.
So we find these like rigid regions, and then we do like
we are not operating with so many new ideas, to be honest.
but we don't have to simulate everything, but we can find a
New algorithms, but new ideas.
that's just from this.
The basic idea.
So you find that,
Unfortunately.
and that's
Actually, all of it.
so all of this
Because I worked, I generated millions of
yeah.
I don't know what you said. When you have like
in contact prediction, I've seen one of my colleagues they get very
Just like
So you know, you lower the pitch and reach some
the good news for me is that
because pH responding to
the
you're not only
good news is well for the last 30 years I don't have to deal with it. So if you find
it's kind of like an experiment. Can you predict it?
and I showed it interestingly enough but I couldn't show yesterday.
So you have that,
So for this part of the pathway, so we
Lately,
have
what could be a precursor of
these are the regions that are quite important.
receptor which
Currently doing
that actually bind
and you haven't shown their
I'm not doing it.
No, no, it's not Montreal. I don't know which side it is. It is 12 South. Accessories for Mac. That's with free background for dual and triple screens. So they have packages that are really cool to download. This is one of them.
It's not open, but
we're going to submit it.
one of the yeah, but it's tricky to be it's a beautiful place to live and work in something. It's not a fire. You got that?
It's a beautiful place.
Many parameters one doesn't.
If everybody can begin to take their seats, please.
Yeah, you just input like the structure and then the regions, like for example, it's loose. So you select certain region, grab it, and then you run it, and then it'll tell you what other regions are in communication.
Okay. Our next speaker is Lousi-Philippe Morency from the Université de Montréal.
Good morning, everybody. As I said, I'm Lousi-Philippe from Raphael's lab in Montreal. Today I'm going to present you my PhD project, which is called The Impact of Conformational Entropy on the Accuracy of the Molecular Docking FlexAID in Binding Mode Prediction. First, we are interested in molecular docking, which aims to find the most stable conformation between a target and a ligand. Target could be any polymer of DNA, RNA, or a protein. ligands can also be protein, DNA, RNA, peptide, small molecule. Although FlexAID is more interested into small molecule like peptide and drug-like molecule. This is more what I will speak about today. This is an animation to explain a little bit how the goal to find the most stable. So molecular docking has three main applications. First is binding mode prediction. The goal is to retrieve what we already know from a crystal. Virtual screening is used, it's a little bit harder, is to find more ligands that will bind the same target once we already know what is binding. So we use a reference and we compare multiple ligands ranked on the same target. And one of the hardest will be the free energy prediction. I will not get into that today. Maybe this project will lead to something closely related to that in the future. FlexAID is a software that we develop in our group. FlexAID stands for Flexible Artificial Intelligence Docking. It is developed in C and C++, and it is available on our website, Biofizz, or on GitHub. It is a command-line executable that can be compiled on Windows, Mac OS, and Linux. There is no dependency that you need to install before compiling FlexAID. And we integrate numerous features that are absent from other software. Some FlexAID features, we use a genetic algorithm to search the conformational space. We employ a classification approach used on PDB bind to determine and optimize the pairwise interaction energy for the atom types. Our atom types are almost the same from Sybil. If you know already, we can simulate covalent binding or constraint docking, and we can also include normal mode analysis to simulate the movement of the backbone of the target. This is still an experimental feature, but this is something that we will look to work more in the following years. We also have a graphical user interface, which is installed as a PyMol plugin, which has two main parts. First, cavity detection. Automatically, you can tell getClef, what it's called. You can ask for as many cavity as you want, and it will find from the largest possible to the smallest possible up to the number you want. So it is easy to define cavities for docking, and it is easy to select one or multiple cavities for docking. We also have the docking simulation in PyMol. You can see in real time the evaluation of your results, as well as their score, and RMSD to reference if there is a reference. Just a single point on that. PyMol, since they switched to the latest version, PyMol 2.0, they modified their graphical framework, and as of now, the energy suite is only compatible with PyMol below 2. We are not yet compatible for PyMol 2, which has been released this year. Oops. Okay, so three objectives motivate FlexAID. One, we want to develop a method that is accessible to the user, so easy to use, but also free, and you can actually compile it and have it on your computer. We also want to develop a competitive software. FlexAID has been published first in GCIM in 2015, and where it stands the most is comparing three scenarios. The three scenarios I will speak more later. From the easiest to the hardest, FlexAID is in red. We can see that FlexAID stands out when the flexibility is the more critical for the docking. But it's also a testing ground for new features and an idea, more like a playground, if we want. Just earlier, I speak about normal mode analysis. This is one of the experimental features that we include into FlexAID. The conformational entropy, which is my main topic today, is also one of these features. First, I will just speak about FlexAID scoring function. Not too much in detail. We use a soft scoring function that is based on the surfaces in contact of the atom. So basically, you can see here a schematic of two atoms in contact, and this is like the surface that we calculate. We have three parts in our scoring function. The purple part will score the contact between one atom and one another. The yellow part will score the contact between an atom and what is empty, what is considered as an implicit solvent. And the third part, the red one, is to prevent steric clashes. So from that, with a pose, we can calculate a CF. That has been in FlexAID already. What is new? So why I would like to consider entropy now? This is an example of a biodine bound to streptavidin, a case which is known to not have lots of entropy, but still. If I run a simulation of FlexAID, and I take all the results that you can see, all the poses that will be predicted, they are colored according to their probability. So the lower their energy, the more the probable, the bluer they are. Actually, FlexAID at first was trained to find the bluest pose. What you could see is, if we look at the energy inside of the landscape, FlexAID will have found the point, sorry for the shaking, the point that is the lower. Although this point will have been here, and in that case, if we can extract that part, we can see that we have some blue poses, but a lot of red poses around. The real solution in that case is here, where you can see a lot of blue poses similar. So the idea is to construct a binding mode, which will be made from multiple poses and will be evaluated together to rank the results, to simulate conformational entropy. So for that, the first part of FlexAID, I won't get into the detail of that, but the first part of FlexAID is density-based clustering algorithm that will automatically create the cluster and will define itself the number of clusters. And for each cluster, we will take every pose in the cluster, and we will first build the partition function. Just highlight the fact that temperature is a parameter that we have optimized with our matrix energy. It appears in the partition function, Boltzmann probability. It appears so here, because it is here, but it will also appear here. I will speak more about temperature a bit later. But first, we will simulate the enthalpy of binding mode by summing the probability of each pose and their CF, the score that is shown last slide. We will now add the entropy of binding mode using Shannon's entropy, which will sum the probabilities and the logarithm of the probabilities. Then we will have a new score, delta G for binding mode, which will be delta H minus T delta S. So the idea a bit is to start, if you want, from a single pose like that with a single energy, and to go out with multiple pose, multiple conformation, and energy that can be separated into thermodynamic parameters. So you can see visually what it does for a ligand and another example. FlexAID outputs the binding modes like that, so you can visually look at them if you're interested. Now I will speak a little bit more about the methodology I will use to benchmark the entropy of FlexAID. So I will use 3 test cases that will be increasingly complex. And for each test case, I will compare FlexAID, FlexAID DS, which is FlexAID with entropy. I will compare FlexX, which is an older method, Autodoc Vina, which is one of the most popular according to the stations, and RDoc, which is a recent method, but is pretty good. And for each method, we will allow 2 million energy evaluation for each simulation on each case. Then we will do bootstrapping 10,000 times to have errors. And we will evaluate a success quite stringently above 2 RMSD, always, no matter how hard the case is. So for the results, my first case is, my first data set is the Aztecs diver set, which is, has been built by Aztecs Pharmaceutical to test their own docking algorithm. But it is mostly self-docking, so it is the easiest case. The target won't move, and we just put back the ligand in the original target. Here you can see at the left what FlexAID reported in the paper, what we have now, which is a slight implementation. What you see in white is the median success rate for this data set, composed of 85 cases. Autodoc Vina performs a little bit better with 82%, FlexAID 78%, and Erdoc stand at 88%. This is the simplest case. This is not where I thought I would see the most improvement with entropy, but in my next scenario, which is cross-docking, it is the Aztecs non-native. This time we take the 85 same ligands, but we will dock them in a conformation that has not been, a conformation of target that has not been crystallized with that ligand. So it is cross-docking. We will need to move sidechain around to retrieve the solution. Complexity goes up a bit. Each case has an average 10 to 24 possible conformation. Just remember that we will evaluate 2 million for each method. So now this time we see a more pronounced upgrade of our precision on the dataset compared to FlexAID normal, and we also see that we are now above Vina. Vina seems to be really good when we use self-docking. It loses when it comes to cross-docking. Erdoc is still really good on the Aztecs non-native dataset. Before going to the next third scenario, third one is more complex again, I just want to speak to you a bit about the temperature. The temperature is not a real temperature. It is statistical weight, more so, which has been optimized independently, and optimized value has been seen in the range of 13 to 21. So for most of my work, I used the temperature of 14, like you see here. Although recently I decided to try different temperature to see how it will improve or not my results. And we can see that there's a slight variation according to temperature, but the best one is at T20. So T20 has been used for the results that I'm showing today. That's it. So now we come to the AP2 dataset. The AP2 dataset is a dataset which has been built by two of my past colleagues in the lab to study sidechain rotations. What is interesting is that there is a critical movement involved in the binding site, in the sidechains, to retrieve the result. So if you don't consider target flexibility, you will fail. And now we still have a more pronounced upgrade of our precision, but also what is the most remarkable right here is all the other ones are less performing. However, my point here is not just to compare to others, not to say that we're better, but my point is I want to show you how we improve just by considering entropy. So just a little recap here of the self-docking, so Aztecs divers, the cross-docking, Aztecs non-native, and the AP2 dataset, which is the largest one. You can see how many possible conformations we will need to try exhaustively if we will be sure, if we want to be sure to find a solution. So, as overall, I would say that the entropy improves FlexAID performances, but the harder the cases get, the more interesting the improvement we see is. And this part is true for the RD case, and I just want to remind you that most of the time that we use docking, most of the time we will use docking on a target that is not really crystallized. Either it will be a mutant, homology model, or simply different conformation. And these cases are harder than even my third scenario. When you dock an homology model, it is really important to take into account the flexibility of the molecule. Also, FlexAID is available at our website or GitHub. The entropy part of FlexAID has now been pushed to the GitHub only. It's not yet on the website, but is accessible via the entropy branch on the GitHub if you want to try it out. I would like to thank ISMB for the travel fellowship, funding, and everybody in the lab, especially my PI, Raphael, and Francis, who contributed a lot to this project both. And you for hearing me out today. I will be glad to take your question.
Question? How are you scoring the different rotamers? If you're doing sidechain flexibility, are you within rotamers or between rotamers?
Actually, we used a list of probable rotamers observed from the PDB, and each rotamer is encoded in a gene. Because we use a genetic algorithm,
right.
So when a mutation occurs, a different rotamer is selected.
Right. So it's by like a log frequency of that rotamer or something, minus log frequency? What's the score on the rotamer?
We don't score the rotamer. We simply score the contact between the sidechain and the ligand.
Right, but if you're going to sample a different sidechain conformation, you want to have an energy for bad sidechain conformations.
We don't take that into account. But if there is any clash, it will be rejected quite harshly.
With the sidechain, with the protein?
With anything. Protein, with an ion, with the ligand,
Yeah.
it will be harshly
Check how
penal.
well you're scoring rotamers versus the rotamer library, either ours or anybody else's, to see whether you're getting a good distribution of those energies versus the frequencies. I would think that would be good.
That would be a good idea.
Hi, yeah. So it was a really cool talk, actually, really, really interesting. So the question I have is, if I understand correctly, when the scoring function for estimating enthalpy was designed, you were using data from PDB bind in order to do that?
Yeah.
That's correct. So one thing I was thinking is what sort of struck me was how significant the difference was between how, for example, the Autodoc Venus scoring function and your model performs when you crossdock. And something that came to mind was PDB bind is quite redundant in terms of multiple examples of different targets. There's some big boys with hundreds of examples, so slightly different conformation of the protein, different ligand. In contrast, Vino was trained on a really small data set with much less redundancy. Do you think that having those slightly different conformations of the binding pocket with slightly different ligands might have allowed you to train, to develop a model which is sort of less sensitive to cross-docking into a slightly different binding pocket than something like Vino, which had less training data?
That's a good question. I will be tempted to say yes. Just want to say first about training data that everything that is in PDB bind that could be seen in that for any method has been removed in the test set. So any method trained on something has not been tested.
Yeah, exactly. No, I was purely in terms of the redundancy in the data set, absolutely not in terms of overtraining.
Our training set is quite large.
Yeah.
It's in thousands of complexes.
Yeah.
So it's,
Yes, I know the most recent version, even if you just use the KI/KD data, is over 4,000 complexes. So it's a lot more data with lots more redundancy. Yeah.
Yeah.
Okay, cool.
The scoring function was trained on a subset of them.
Okay.
With redundancy removed.
Okay, so what, single example of target?
Yeah, there were some thresholds for sequence identity and ligand identity.
Okay, so you didn't have multiple examples of different conference. Okay.
But what LP didn't have time to show is the way we trained that we had an ensemble of true positives, which were the crystallized structure plus a low energy set against further away decoys that are negative set, and this was done interactively.
Okay, cool. I mean, that could also be quite interesting. So if I remember, I don't know about the other docking software, but certainly with Vino, which did far worse, as far as I understand, that was just trained against crystal poses for a few hundred protein ligand complexes. So that could have made a big difference.
It was turned into a classification.
Yeah.
It was turned into a classification question.
Cool. Yeah, that's really interesting. Thank you.
Okay, on your first slide, you showed docking of biotin to strapped avidin, and you showed quite a diverse, poses. And I'm wondering how you actually did the calculation, because biotin is a tetramer, and the binding site is actually quite constrained. So if you use just the crystal structure, 1 STP, then you will have the diverse. But so I was wondering what structures you used.
It was done on the monomer.
Okay,
So
right. That would explain
that is a good point.
Right.
Doing it on the tetramer will maybe led to the good solution. But the point with the slide was not just to show for binding, but this is common for many binding sites.
Sure.
You see spot of blues, if I retake my example, and we want to score which one of these area is the more favorable, if we want, energetically.
Right, thank you.